Really. So we wait for the audience to join.
So you really did want the talk to be 1 hour long and then plus an extra half hour for questions?
Yes.
Okay. And do the people ask questions, or do you need to ask some questions first in order to warm up the crowd?
Usually I will ask a question or two just to warm up, and then I encourage others to ask themselves. But most of the
Right,
time, they just chat it out, type it out on the chat box.
right. And as I said, I will not see the chat box.
Yes. I'm here for that. But incidentally, may I ask, what happened to DEC? Are there any tidbits of them around?
What happened to what?
DEC.
Oh,
Digital.
DEC, Digital Equipment Corporation.
DEC,
Yeah, I left before it imploded, but I think lots of different pieces got sold to different places.
Oh, so there's nothing left of it.
Right. So
Okay.
part of it was bought by HP.
Recording in progress.
Whoops.
Okay.
Yeah. So right, Digital Equipment Corporation does not exist anymore.
Yeah, okay. They were quite huge at one time.
Yes.
I think.
Yeah, one of many companies I put out of business, like Sun.
Can I say they were on par with they were the Dell of the 80s?
Sure. But hopefully you're not jinxing Dell by saying that.
No. I'm not saying that. No. Touch wood.
And the audience is primarily students, you said?
No, I think mostly staff.
Ah, okay.
I doubt students will join this week because it's exam week.
Ah, okay.
I
Because
don't know. Maybe postgrads will join.
right. I sort of tailored the talk to some advice for students.
Yes.
It should be fine.
Yeah, it should be fine. Even most of our staff are in the mid-30s, 40s. Okay. Oh, okay. We're reaching 40s. Latest statistics. And may I ask about your name? I can't place it. It's not American. It's not French.
Right. My parents made it up. So apparently, according to Jewish tradition, you
Okay.
just need the first letter. And
Okay.
I was being named after my grandfather, whose name was Reuben. So
Okay.
they used a Scrabble set and put an R down and then played with the letters and came across Radia. And they liked how it
Oh
sounded. It
man,
sounds like a name,
you're
and
the
it
first
sounds
one from the
like
Scrabble that I know.
right. And so it's sort of like for radiant and radar, radius, all these things.
Okay. All right. Okay. That's nice. That's cool. That's totally cool.
I'm really pleased I didn't have any blanks in my name.
Like what was this guy? This Canadian comedian, stand-up comedian. Was it Russell Peters? He used to joke that he met an African guy with was it an exclamation mark on his name? And the pronunciation goes with the tick. Hmm. Is it Shah not playing the video?
Not that good.
Oh, no, playing.
This is like okay.
You want to test your slides, Radia?
Yeah, can I start sharing?
Yeah, sure. I think
Yeah.
Are you seeing it? Do you see my slide?
yes, yes. Is
Oh,
there?
okay.
Can you
So should I just leave it up there?
can you just cycle through one or two? Yep. All right. Nice. It moves. Cool.
Yeah, there's a funny story about my name. I assume if you post it, you'll trim off the beginning here. Is that true?
Pardon? Pardon?
Oh, if you actually post this, you're not going to post this chatting beforehand. You'll start it where the lecture starts.
No, I don't get what you're saying.
Oh, well, because you started the recording already, I hesitate to tell you another
Oh, okay,
funny
okay, okay,
story.
okay. Oh, okay, okay, okay. Yeah, I think we missed that. Yeah.
So when you post the recording, it will start when the lecture really starts, not now, right?
Yes.
Yeah, but we will edit the
We'll edit.
we will edit your video.
Yeah.
Okay. So
So
if we want to spend another minute or two, I could tell you another
yeah.
story about my
A
name.
few more
Okay.
minutes. Yeah.
Few more minutes.
So before I was known, early in my career, I was an ACM lecturer, which means you volunteer to give talks at very small colleges that wouldn't ordinarily get good lecturers.
Okay.
And then if a college requests somebody, then ACM pays their travel. So any college won't get to have a lecturer more than once every 10 or 15 years. So the computer science club of some college looked through the book of abstracts and whatever and chose me. So the faculty advisor saw my name and didn't recognize the first name and was thinking to himself, oh no, I don't want to waste our one opportunity on one of these foreigners that can barely speak English. And he didn't want to say that aloud. So he told the students to call me, which they did. And then they said, okay, we called her and we still want her. And the faculty advisor said, "How did she sound?" And they said, "Oh, I don't know. She sounded nice." And then he said, "Did she have an accent?" And they said, maybe New York. So,
What he meant was national accent, and they went for
right, right.
regional. They went for regional accent.
Yeah. So he
Good,
let
good.
them have me, and
All
it was
right.
fun.
Okay. Did you meet him after that?
Yeah, sure.
What do you do at Dell nowadays, Radia?
Well, a lot of things. My favorite way that the CTO who hired me introduces me is as Dell's bullshit detector. And I design things. I collaborate with groups. I I learn weird things like quantum that are hard for people to learn, and then I give talks so that they can easily understand things. Um, I mentor people.
So it's more on what do you call mentoring what do you call more of a mentoring task. Uh, not you're not involved so much as in the nitty-gritty of stuff.
Well, I do, learn about products and what problems they would like to solve, and then I help them
Okay.
solve it, and I
Okay.
design sort of new things. Yeah.
Okay. Oh, that's cool. So where are they headed? I don't see Dell making any big announcements like Microsoft or uh, IBM or those guys. Are they headed towards the quantum way? Are they headed?
Are you asking me something?
Yeah.
Oh, um, yeah. I mean, the world is, actually making progress on building these things, but it's not clear what they actually could usefully solve, other than breaking our current public key algorithms like RSA. So the world is busily coming up with new algorithms that a quantum computer would not be able to break. Currently, like with RSA, which is something we use a lot, if I know your public key and I have a large enough quantum computer, I can
Yeah.
compute
Yeah.
your
Yeah.
private key. So that would be like very bad. But they're coming up with new algorithms. So actually, our book, the third edition of our security book, talks a lot about exactly what a quantum computer can do and can't do, and how it manages to factor numbers, why that breaks RSA, and intuitively what some of these so-called post-quantum algorithms are. I hate the term post-quantum because it sounds like, once everyone has quantum laptops, then you worry about these things. But no, it's something we'll be doing, the industry will be doing very soon.
Yeah.
So, Radia, you are now working on cybersecurity?
Yep.
Oh, okay.
Where is that? Dah cukup orang. 31. Oh, I will start now. Just give me a few minutes to introduce and then I'll pass the floor to you. Okay, salam sejahtera, selamat pagi and a very good morning to all gathered here virtually. We are here for Cosmos of Curiosity Series 31. Thank you to Unimap Faculty of Intelligent Computing, Dean and Broadcast Control Team, here led by Mr. Shah Rizan for hosting this event. I'm Prabha, your moderator for this series with the title Myths, Missteps, and Mysteries of Network Routing and Bridging. I use the British routing instead of the American routing. Before we begin, I would like to introduce our esteemed speaker for today, Dr. Perlman, fellow of Dell Technologies. Radia Joy Perlman started in the field of computer networks at the ideal time, the dawn of the internet. Dr. Perlman obtained her Bachelor of Science and Master of Science in Mathematics from MIT, and later a PhD in Computer Science also from MIT in 1988 on routing in environments where malicious network failures are present. Her contribution to the computing and network world is on how to make networks self-organize, to calculate how to route data. Her design of this in the 80s remains widely deployed today. She also designed the spanning tree algorithm, which enabled Ethernet to evolve from a single shared link to a network that could support many hundreds of thousands of computers, and is actually how modern day Ethernet works. This was achieved when she was at Digital Equipment Corporation, DEC. She wrote the textbook Interconnections. She wrote the textbook Interconnections, Bridges, Routers, Switches, and Internetworking Calls and Communication in a Public World. She has received numerous awards, including the induction into the Inventor Hall of Fame, induction into the Internet Hall of Fame, Lifetime Achievement Awards from Association of Computing Machineries Signals Interest Group and USNICS, election to National Academy of Engineering, election into Washington State Academy of Science, and an honorary doctorate from KTH. Good evening, Dr. Radia. Hope you've had a great day. And I pass
Thank
the
you
floor
very
on to you.
much.
Thank you.
Okay, so I should just start. By the way, the interconnections, the publisher really wanted me to say something about internet in the title. At the time, I really hated the term internet because to me, if you have two networks and you plug them together, you don't get an internet, you just get a bigger network. But at any rate, so at the host's request, in addition to technical stuff in this talk, I'll discuss some of my history and some advice for students. So am I an engineer? So the stereotype of an engineer is that they're just busily taking things apart and fixing things. I never took anything apart. I always assumed I would get electrocuted or I would break something. But I have some superpowers. So my first superpower is a tiny memory. I can't remember very many things. So some people in class can remember what the teacher said and repeat it on a test. I can't do that. I have to be able to derive things in real time from the three things I can remember, which means that I have to understand things very deeply and not get distracted by details that are irrelevant to the conceptual heart of the problem. So my second superpower is that I hate computers, which means that I design things for people like me, meaning, that you just plug it together and they work. So once I was told when I was at Digital Equipment Corporation and I was designing stuff like that, someone said, but we have customers that like to configure things. And they think that the stuff I do was boring because you just plug it together and never think about it again. So I said, fine, if they want knobs, I'll give them knobs, but you don't have to touch the knobs. And even if you do touch them, you can't hurt yourself. Any setting of the knobs will work. You might be able to tune it to work a little better in some cases, but you don't need to. And my third superpower is skepticism. So I need to deeply understand something before having an opinion. when there's a lot of hype about something, it tends to make me even more skeptical. And I seek out people who disagree with me and listen to what they have to say. And, often they're not correct, but I have to, hear them out first. So how did I wind up designing routing protocols? It was just a bunch of random events. Um, so, I never would have planned my career this way, but I'm happy with how it turned out. So in high school, my goals were just to get really good grades, get into a prestigious college, et cetera. There was no one thing that I was really passionate about. I was, interested in everything. I liked the science and math classes because the grades were predictable. All you had to do was understand the material and you would get a good grade. Whereas in English, and I did really love writing, you couldn't predict what mood the teacher was going to be in and what grade you were going to get. I hated history because the way it was taught was all memorization, memorizing meaningless names and dates and whatever. My mother would help me memorize what I needed to do for the test, and I would get 100 on the test because I spent so much time memorizing it. But then 10 minutes after the test, it was all gone from my mind because I couldn't store that meaningless stuff. And sometimes my mother would say, oh, there would be something on the news. You were just studying that in school. And I would look at her blankly because it was all gone. So although I kind of knew I would be the best student in any math science class at my school, I wasn't actually even happy about it. I had a fantasy that some boy would do better than me at some math or science thing. And my fantasy was that I would fall in love with him and marry him. Anyway, the reason that I'm telling you that is how I got introduced to computer programming. So in high school, there was a teacher that noticed that there was a computer programming class at a nearby college, and she could sign a few of us up. She would drive us over there in her car, wait for the class to be done, and then drive us home. I mean, teachers are just awesome. She was not paid to do this. So I walk into this class, having always known beforehand that, sure, whatever class it was, I would do fine. But my perception was that all the students were bragging about how they were able to build a I forget the name of it, a ham radio when they were like 7. I had no idea what a ham radio was, much less think that I could be able to build it. And then they were asking questions with fancy words like input, which I had no idea what that meant. And so for the first time, I got 0 out of that class. So at that point, if you asked me what I wanted to do for a career, I would have said anything as long as it doesn't involve computers. So college, I majored in math. And yes, back then there were basically no women, especially in math, but mostly I don't notice these things. But there were some awkwardnesses. So I realized that all these boys were incredibly shy, vulnerable, sensitive people. And if I were to so much as like look at one of them, they'd get all excited. It's like, oh, I'm going to get married now. And I didn't ever want to hurt anyone's feelings. And that was very awkward. There's this famous computer science problem known as the dining philosophers problem, which it's just sort of a cute way of phrasing the problem, but it's that you have a bunch of processes, each of which need certain resources. They need to lock a file, they need the printer, whatever. And if you just have each one of the processes try to gather as many resources as it needs and then wait, you can have a deadlock because all the other things you need are locked by other processes. So I sort of discovered a new way of solving this problem. I was taking a digital hardware class at MIT, and of course I was the only woman in the class. And the hardest thing about the class was there just wasn't enough equipment. So in order to get your project checked off, you had to go around to the other students and say, oh, do you have any extra AND gates? Can I borrow your oscilloscope? And I realized, kind of to my horror, that there wasn't anything I could ask these, very shy boys that they wouldn't say, oh, take it. Can I borrow your oscilloscope? Sure, have it. Do you need a kidney? Whatever. So I got my project checked off really quickly, and then feeling a little guilty, I I decided I owed it to the world. So I would pick some kid in the class and I'd say, okay, what do you need? And I would go and gather it for him. And then he'd be checked off and he wouldn't need any of the equipment. After I did that for like 6 of the other students, there was enough equipment that the rest of them could work it out themselves. So my novel solution to the dining philosopher's problem was introduce a woman. So how I learned to program, I was taking a physics class and I was doing well in it. And the TA said to me, hey, Radia, I need a programmer for my project. Would you like to be my programmer? And I said, well, I don't know how to program. And he said, yes, I know. That's why I'm asking you, because I have no money to pay you. And if you knew how to program, you'd expect to be paid. But you're obviously bright. I'm sure you could learn. And the reason I agreed to do it, to be brutally honest, is that my boyfriend at the time did know how to program. So I figured he could help me, or he could just do it if I couldn't learn. But yeah, so I learned to program. It was really fun. That was back in the days of assembly language, which is how I like to program. It's, there's only 10 instructions, no operating system to worry about. You have the machine to yourself. So then I went to grad school, and I knew how to take classes. This is what you would expect. I would go to grad school right after undergraduate. I did everything but a thesis. But my perception at the time was that everybody else got into graduate school because they were smart. And I had just gotten into graduate school because I studied really hard. And if they realized how hard I studied to get those grades, they never would have let me in. I had no idea how to do original research. I assumed just some other species did that. So when around that time, the MIT math department, you had to find your own advisor, and I was too shy and insecure to do that. So an old friend asked me if I was enjoying grad school after I did everything but a thesis. And I said, no, I'm kind of floundering. I have no idea how to get an advisor or a topic or anything. And he said, oh, come join our group, our company, which was at the dawn of computer networks. And it was at a company called BBN, which was a company that was building stuff for the government. And I wound up designing routing for the ARPA packet radio network. And I loved it. It's this concept that you have all these little computers doing stuff based on what they know locally, and somehow it all fits together like a beautiful symphony. But later I got the absolute ideal job, which was designing routing for Digital Equipment Corporation. And that was such an amazing experience. These days, to do anything, you have to fight with a standards body and things like that. Here, it was kind of a green field, and I was the only one designing routing. So whatever I designed just got implemented. So my protocol for routing was unfortunately called ISIS, which IS stands for Intermediate System, which is their term for a router. And so it's the protocol for routers to talk to each other. So what's sort of funny about having been called ISIS is, I don't know, like 8 years ago or so, Trump said that Hillary and Obama had invented ISIS. And that was a headline in some newspaper things, which I wasn't even aware of. But people forwarded that to me and said, shouldn't you get some credit? So anyway, Later, the Internet Standards Organization, which is known as IETF, they mostly just copied IS and they called it OSPF. So the main concepts in OSPF are also what I designed. And the implementers got tired of having two very similar things. And so they merged the two and they just call it LSR for link state routing. So the second time, 10 years later, for very weird reasons, I did go back to grad school and I did get my PhD this time in computer science rather than math. Oh, there was this great story. So my daughter was like 6 at the time, and she was really proud of me for going back to grad school. She had no idea what any of it meant, but she was playing at a playground in Cambridge, Massachusetts, and she was playing with this other little girl, and she said to the other little girl, "My mommy's going to get a PhD from MIT." And the other little girl said, "My mommy already has one." She had a PhD in chemistry. We got to be friends. So grad school was so much better the second time because I had learned secrets. Like when the professor is droning on, ask questions. And, when I went the first time, I kind of assumed that everyone in the class was following and it was only me that was lost. But no, I can tell when nobody's understanding them. And when you get a problem set, start as soon as you get them rather than in a panic the night before it's due. And if you've done the homework and followed the class, you'll do fine on tests. Whereas, the first time I was always incredibly panicked when I first saw a test because I thought the professor was trying to trick us somehow. So network layers. So the way that people learn about network protocols is they always start with layers. So it's a way of learning about networks. Actual networks don't strictly following layers, but it's a good way of thinking about things. So the concept is each layer uses the services of the layer below, and it adds functionality to present to the layer above. So in theory, doing it this way allows each layer to be independently replaced as long as it provides the equivalent service of whatever it's replacing. So strict layering would say that layer N does not look at information in headers other than layer N, but in deployed networks, it's usually violated. For instance, routers, which are layer 3, they usually look at TCP ports, which are layer 4, to ensure that packets from the same flow go on the same path so that they don't get out of order. But again, layers are just a good way of learning about networks. So the layers relevant to this talk. Layer 1 is the physical layer, which says, how do you send a bit to a neighbor? So it says, what's the shape of the cable, that kind of stuff. Data link layer, or layer 2, is how to form the stream of bits that you get from layer 1 into packets so you're sending 0, 1, 0, 0, 1. Somehow you have to signal within that stream, this is the start of the packet, this is an end of the packet, this is a checksum. But the important thing is that layer 2 is only for talking to a neighbor, someone who's on the same link as you. Now, if you have a multi-access link, it might involve adding more information like the source address and the destination address. Layer 3 is the network layer, where the header specifies who the ultimate source and the destination is so that the data can be sent across a path consisting of multiple links. So we have two headers, layer 3 and layer 2. So when S transmits a packet to D, the destination will be D and the source will be S, and that header stays the same through the entire journey. But there's an extra header, which is just for each link. So in this case, the destination will be beta and the source will be alpha. And then on, and it does that hop by hop. But if you have a point-to-point link like here between R2 and R3, you don't need a header. And, then the next hop, it says that the destination is this guy and the source is this guy. And then when it gets to this guy, the only thing that matters is this part. But suppose the network were built all of point-to-point links. Point-to-point means just there's two nodes on it. So it's just between two computers. Well, in that case, this extra header is completely unnecessary. Why do you need to do that if there's only two nodes on the link? So really that header should be unnecessary, and you should just be able to say the source is S, the destination is D, and everyone should just forward it. So why do we need both Ethernet and IP? And I'll talk about that later in the talk. So what are routing algorithms? By the way, I use routing and routing interchangeably. Routing algorithms are supposed to be layer 3. So a routing algorithm says that there are these switches that you can call routers or switches or bridges, whatever you want to call them. They're components that forward packets from link to link. So it receives a packet and it looks at the destination address and it looks in its forwarding table, and the forwarding table says which cable to send it to for each destination. So how does it get this forwarding table? Well, there are routing protocols, and a distributed routing protocol is one where all of the routers are participating, as opposed to something where all the routers let a central node know what who its neighbors are, and the central node computes paths and forwards it, configures all the routers. So in a distributed protocol, routers communicate with their neighbors because you can't really talk directly with anyone else. And you exchange information and you use local information that you've been configured with, such as the cost of links and what you've learned from your neighbors to calculate the forwarding table. So the kind I like best is called link state routing. And that's what I used for DECnet. The first link state algorithm was for the ARPANET. So when I joined and I told my manager I want to use this algorithm for DECnet, he said, well, I was never convinced that that was stable. If you can prove that it's stable. And indeed, I'm much better at counterexamples than I am at proofs. And I realized that, no, it wasn't stable. And I'll talk about my first paper there. So link state routing, you meet your neighbors, you construct a packet that I call a link state packet that says who you are and the state of your links, a list of who your neighbor is and the cost to that neighbor. And you broadcast that to all the neighbors. You store the latest link state packet from each router, and then you compute routes. Once you've done that, you know the whole topology, and you can compute paths from yourself to everyone else using an algorithm due to Dijkstra. So this is a network here, and these are all the link state packets that each router would have. So the one from A says he has a neighbor B at a cost of 6 and a neighbor D at a cost of 2, and so forth. All of the routers have this same database, and they use Dijkstra's algorithm to compute paths from themselves to each destination. But there's more to link state routing than Dijkstra's algorithm. How do routers reliably flood their link state packet? So security and robustness. What happens if things get into bad states? If your PC gets into a bad state, you reboot. But what about a computer network? Well, computer networks problems tend to be diagnosed and fixed by sending messages on the network. So what if the network is broken? So one of my first papers was noticing that the ARPANET algorithm was really fragile. A few bad link state messages and the network would never recover. So my paper said networks need to be much more robust than a PC. And I called it self-stabilizing, that once you get rid of whatever node is generating bad packets, the network should return to normal operation. And I explained how the ARPANET, what the failure mode was, and I showed how to design such a network to be self-stabilizing once whoever was causing corrupted messages was disconnected from the network. So the paper was actually rejected, which got me very discouraged. I wasn't in academia at the point, so I had no advisor to tell me not to worry. But it had two reviews, one that said it was a really good paper, and the other one, which even though the reviewers are anonymous, I could tell it was one of the people who had designed the ARPANET algorithm who was feeling, um, that I was attacking his algorithm. So the review said, it was ranked from 1 to 5 at on a bunch of things, which meant he was saying that it was badly written, it wasn't correct, it wasn't original, and the author was ugly, anything he could think of saying. So I felt like at that point, I knew that was very unfair, but I figured any routing paper would get sent to him because there were so few people that were into routing, and he would reject anything. So luckily, the other reviewer had to have been this famous professor who I had never met, Misha Schwartz at Columbia. So Misha Schwartz contacted me and said, "Oh, you wrote this paper, and I'm using it in my class. Can you give me a proper bibliographic reference?" And I said, "Oh, it was rejected." And he said, "Oh, yeah, that happens all the time. Don't worry about it. Would you like it published in my journal?" Which was a much more prestigious place than the conference I had done it. So anyway, I realized that papers, whether they get accepted or rejected, is almost random. So anyway, I mean, you should look at the reviewer comments, and if there's anything useful in there, by all means, revise your paper. Or if the reviewer is confused, you can make your paper a little more clear. Anyway, so then after the paper was published, that failure mode actually happened in the ARPANET. So what was this failure mode? So in order to flood link state packets, if you receive a link state packet from some neighbor, you see if it's more recent than the one that you have stored. And so if it's from source Fred, let's say, and you get it via neighbor N, if this link state packet is newer, replace the stored one and flood the new one to all of the neighbors except the one you got it from. But how do you know if this is newer? You can't assume that the most recently received is the most recently generated. So you need a sequence number. So how big should the sequence number be? Well, given that you're only going to allocate a finite set of bits, then what you need to do is use modular arithmetic. So with the ARPANET flooding algorithm, it says, look at the sequence number, and if it's newer, then replace what you have and otherwise throw it away. So now how do you compare sequence numbers in a circular space? Well, you start at 0 and you go around till the highest number, let's say n-1, and then the next higher one is 0. So to compare two numbers, if you have a number x, you divide the circle in half. All of these are considered bigger than x, and all of these are considered less than x. So the ARPANET disaster, one day, let's call the router Fred, was not feeling well. And in his dying gasp, he said, "Oh, I curse you, O world," and started generating link state packets with random sequence numbers. So the symptom was just that the network didn't work. They couldn't get any information because the network wasn't letting them talk to anything. So at this point in time, these guys were really lucky because the same guys who designed the algorithm wrote the code and managed the network, all from BBM. So they were called at home saying, "Help, the ARPANET isn't working." And I'm sure they were annoyed that why didn't you just check the, whatever filters. So they came in and indeed it wasn't working. So they rebooted their router and it didn't help. So they did a core dump and they discovered that all the queues of their local router were filled with link state packets from Fred with sequence numbers X, Y, and Z, such that X was less than Y, was less than Z, was less than X. So what now? even if they rebooted their router, it wouldn't help. It would instantly get polluted with these link state packets and immediately try to juggle them. So given that networks don't have on-off switches, what they did was they crashed their local router and reloaded it with a patched version of the code that specifically ignored packets from Fred. They were lucky because there were only about 100 routers. They were all identical hardware running identical software. So yeah, they created a patched version of the code to ignore link state packets from Fred. One by one, they crashed routers, and then they told the router with the new patched thing to tell its neighbors to crash. And that was hard because the neighbors were so busy juggling link state packets from Fred. Eventually, they would get a word in edgewise and say to the neighbor, please crash. And they would load them up with the patch. And only after they had loaded up everybody with the patched version of the code could they then reload them with the real code and let Fred rejoin the network. So this did not happen by somebody doing it on purpose. It happened because of a flaky router. So the improvements I made the sequence number large and linear, but no matter how large the sequence number it is, if Fred is feeling cranky, Fred can issue a link state packet with a very large number. So I also had an age field, which was like a few hours. And if Fred's link state packet reaches the highest value, Fred has to stay offline until everyone ages out his link state packet and he can start again at 0. And this is a much better failure mode of just having the router that was sick anyway, having to remain offline for a while, than having everyone madly juggling Fred's link state packets. And I also did a whole bunch of things to make it more resilient and efficient and so forth. So my paper said this design will be self-stabilizing once whoever is issuing bad link state packets is disconnected from the network, but you can't expect a network to work while somebody is corrupting packets. So my manager at Digital, who was very smart actually, told me, hey, why don't you prove that last line in your paper that you can't do it, or design something that does work. So that was my thesis topic, was to make a network work even if some of the routers were being malicious. So a normal failure is where something instantly crashes and it stops doing things. A Byzantine failure is where something continues doing stuff, but it's doing the wrong stuff. So what can a misbehaving router do? It can give false information in the routing algorithm. It can flood the network with garbage. It can forward packets off in the wrong direction, resetting the hop count, or it can do everything perfectly, but some router doesn't like some source 12 hops away and throws away its packets. So it's doing everything perfectly for everybody other than S. So the goal in my thesis was that as long as one honest path connects A and B, they should be able to communicate with a fair share of bandwidth. And everyone agreed, oh yeah, that's really difficult, really important. And I've never done anything difficult. If you look at things from the right angle, suddenly it's very simple. So then I realized, oh my gosh, I know just how to do it, but it's really simple, and I'm not sure they would give me a PhD for this. So I asked a professor, is there any minimum length to a thesis? And he said, well, it either has to be long or good. So anyway, years later, someone told me they had a system for proving protocols correct. And since I design protocols, I should use their thing. And I said, well, have you proven anything, real correct with it? And he said, yes. He proved the ARPANET algorithm for distributing routing information. And I said, but it's not correct. And he said, yes, it is. I proved it was correct. And I said, but if you inject a couple of bad packets, the network is down forever. And he said, well, if you put in bad data, what do you expect? So um, proofs are nice, but don't assume that since you've proven something about it, that means the system is correct. And something like a network, if there's a whole bunch of components, undoubtedly some of them are going to be flaky and not do the spec exactly. And if that causes the whole system to be uh, to die, that's not a good design. You have to take that into account. So there are all sorts of weird problems that proofs might not notice. So Byzantine failures, like the ARPANET routing, or side channel attacks. And so these are really cool, where a cryptographic algorithm might be correct in theory, but an implementation might leak information about the keys. And there's been all sorts of demonstrations of things that they just monitor the power or the memory uses, and they can then figure out what the private key is. Now, humans are another interesting piece of a system. So let's look at TPS, where the theory is beautiful. The client says, gives a DNS name and says, prove you are this DNS name. And the website sends a certificate stating what its name is and what its public key is. And they do all sorts of cool cryptography. And then they wind up with a cryptographically protected conversation. So that's the theory. But in practice, usually a user doesn't start out with a DNS name and instead does a search and gets some sort of obscure URL string, such as that. That is an actual URL, which no human should ever have to look at. But even if the user finds the DNS name in the URL, I fell for a scam recently. I wanted to renew my driver's license. I knew it could be done online. I'm a human. I don't know the DNS name. So I did an internet search and I got search results. I clicked on the top listed site. I understand the underlying protocols in the crypto, but it didn't occur to me that the top search wouldn't be correct. So I wish I had taken better screenshots before they shut down this scam. But by the time I did it, the only things that were up at the top that were scams said add at it. And they had some sort of perfectly reasonable looking DNS name like washingtoninformation.org. So once I clicked on it, it was a beautiful site. It was very well organized. And if you look how happy the people in these photos are. It couldn't possibly be a scam. So I clicked on renew driver's license. It asked me everything I expected, which was my license number, my address, and my credit card. And so success, I thought I had renewed my license. Now, I would have thought nothing of it. I would have wondered in a month or so why I didn't get my new license. But as it turns out, the bank fraud department called me. Bank fraud departments are incredibly good. So the criminals who put up this website were too greedy, and they kept charging more and more on my credit card. So the bank said, "Are these legitimate charges?" And I realized what must have happened, and so the bank disallowed the charges and gave me a new credit card number. So I was not harmed in any way. And it gives me a fantastic example. And realizing that there's no actual security on the internet because there's this assumption that the human will know the DNS name. And there's no reason to believe that. So don't blame the user. Scam sites can appear first, either because they pay the search engine companies or because they understand the ranking algorithm and they can game the system. This particular scam at that time had several names for all 50 states, like WashingtonLicensing.org and IdahoLicensing.org. And somebody told me, well, you should have realized that it would have been a .gov DNS name, not a .org. And no, I claim I should not need to know that. I'm a human. So once I realized it was a scam, how do you report it? And I had no idea how to do that. But apparently somebody eventually figured it out, and that scam got shut down. So the site I should have gone to was DOL, Department of Licensing.washington.gov. And why should I know that? So another example that I ran into recently was I actually started with the DNS name, which I knew, and I typed it in. It's a company I buy shoes from every few years, and I misspelled it. I mistyped it. So the site looked exactly like it always did. I picked out shoes and I typed in my credit card number, and almost immediately the bank fraud department called me and said, did you, somebody downloaded your credit card into their Apple wallet or something. And did you recently use your credit card like at a restaurant where someone might have stolen it? And I said, no. And then I said, oh, actually, I did buy shoes, but I know it's a legitimate company because I buy from them every few years. And then I looked and I had mistyped the thing. So I'm sure the criminals in this case owned that DNS name. They bought the DNS name, but they just predicted a misspelling that people would be likely to do. And they completely mirrored the site. So they had all the same shoes, all the same prices, so notice there is zero actual security on the internet, even though there's fancy cryptographic algorithms that come with security proofs and protocol standards that took decades of meetings and zillions of drafts and versions to sculpt the protocol, and formal proofs that the protocol is correct, and formal proofs that the implementation correctly follows the specification. But there's this assumption that humans will magically know the DNS name they need to talk to. So in my book on security, I wrote this paragraph. And once I wrote it, I said, yes, that's exactly right. And I've seen it on quote boards, which I'm very proud of. So humans are incapable of securely storing high quality cryptographic keys, and they have unacceptable speed and accuracy when performing cryptographic operations. They're also large, expensive to maintain, difficult to manage, and they pollute the environment. It's astonishing that these devices continue to be manufactured and deployed, but they are sufficiently pervasive that we must design our systems around their limitations. So back to network routing. How do you make networks very large? You break it into pieces, otherwise known as hierarchy. So the post office, you can't just say, this goes to Radia Perlman. You can't expect the post office to know that. Instead, an address contains what country it's in, what state, what city. And within a city, the post office needs to know about all the streets. But outside the city, the level of routing just needs to know how to get to the individual cities. And, if it's a different state, just knows how to reach different states. So no router needs to have an unworkable routing table size. So if addresses are configured sensibly, a destination in the forwarding table can be a prefix like all addresses that start with 387, rather than having every address be in the forwarding table. Quickly matching a destination address to the longest matching prefix in the forwarding table is, another cool thing, but we won't go into it. So parameters. I hate computers, as I said. I design stuff for people like me, and I try to avoid having parameters. So sometimes the committee can't decide what the value is. So they say, oh, well, let's let the user configure that. And no, if the committee can't figure out a reasonable number, why do you expect the humans to? For instance, the link cost. Novell did something very cool with link costs, which are something that's usually configured. When a router would come up, it would send a few messages to a neighbor and measure the round trip delay and the bandwidth and throw it into an equation and get a number. So that's nice. It just, nice not to force people to have to understand all these parameters. But if you have to have a parameter, make sure it can't be set correctly. So obviously, if the only legal values are between 30 and 40, you should not let someone configure the parameter to 920. So that's easy enough. But sometimes you have a parameter value that's legal at A and legal at B, but the values won't interwork. So an example of that is what I designed for the ISIS hello timer, which is how long your neighbor should wait before deciding that you're not there anymore. The hello timer is sort of a keep alive to reassure your neighbor that the link is still working and you're still alive. So this is something I was never able to explain to my otherwise bright college-age son, which is that there is no such thing as a reliable, "Hi, I'm dead now" message. So you have to periodically call your mother. And here's an opportunity for a parameter mismatch, which is how often you call your mother and how long she waits before calling the police. So what I did in the ISIS thing was in the hello message, it says, "Hi, I'm your neighbor. Expect to hear hellos from me every 30 seconds." And your neighbor multiplies that by 3 and decides the link is down if it hasn't heard from you for that time. Now, when OSPF copied it, they saw where you report what your hello timer is, but what they did was they said, when you receive a hello from your neighbor that says that it sends hellos every 25 seconds, you compare it with your own configured hello timer, and if they're not identical, you refuse to talk, which makes the network very brittle. Why shouldn't you have different timers? And if you ever decide to change a timer, then the network breaks, because once you change the timer, none of the neighbors will answer. They'll all break the links. So I've been complaining at them about all this for decades. And what they have said was they think their way is simpler, but at any rate, books. So it changed my career. I'm not very good at looking or acting important. And so I happen to have written these 2 books. So Interconnections, I wrote by myself, and Network Security, I co-wrote with Charlie Kaufman. And the 4th co-author, interestingly enough, is my son, who's one of the world's experts at quantum. And therefore, in this edition, we talk a lot about what a quantum computer is and what the new algorithms are. And we wouldn't have had the nerve to attack this without having, such an expert. Now, he can't explain anything, so I do most of the writing because I have kind of a way of making things concise and understandable and a little bit funny. But yeah, he was very valuable. So it's very hard to succeed to do the same thing I did, which was become well known with books today, unfortunately, because people expect all information to be free on the internet. But don't get discouraged. It's not worth writing a book just for the money, for royalties. The amount of money that I made on the books, if that was why I was writing the book, I would have done better working part-time at McDonald's, but for the hourly rate. But it was very educational, to really think things through, to decide how to explain them. I learned a lot from doing it. And for me, it was great for my career back when books were how people learn things. But today, there are other ways to achieve the same thing. You can do online tutorials or talks at your company, or do a book online that's free. And then again, you'll get well known if you do a good job of teaching these things. So now back to the question, why do we need both IP and Ethernet? So the answer that everybody knows is that IP is layer 3 and Ethernet is layer 2. Now, what does it mean to be layer 3 versus layer 2? So remember the layers, which I talked about. layer 2 is supposed to be sending a packet to a neighbor, whereas layer 3 is supposed to be something that creates a whole path. What layer is Ethernet? It was intended to be layer 2, which was just neighbors talking to neighbors. But we're forwarding Ethernet packets today. So how did that happen? So I claim Ethernet today should really be considered layer 3 because it's hooking together a whole bunch of links. So back then, I was the designer of layer 3 of DECnet, and then along came the Ethernet. So the original Ethernet was a way for a bunch of nodes on the same wire to share the bandwidth. And, if there's more than one guy speaking at the same time, the receivers just get garbage. So the protocol was known as CSMA-CD, carrier sense, which means listen before you start speaking, don't talk if someone else is talking. MA is multiple access, lots of nodes share the same wire. And collision detect, that means that you listen even while you're talking in case someone else decides to talk at the same time, in which case you both stop and you start a random time later. And there were all sorts of papers about how much you could load the network with before there were too many collisions. So it was limited in terms of the number of nodes, maybe hundreds of nodes, and the distance. So it was okay to hook up a building, but it was not good for the internet. So now some interesting things. Ethernet has a 6-byte address, and it only needs to identify nodes on a single link. And there were only like a few hundred nodes on any Ethernet, whereas IP had a 4-byte address, and it was intended to identify all nodes in the internet. So why would the Ethernet designers use a 6-byte address when an Ethernet only supported a few hundred nodes? Well, this was kind of one of the geniuses of Ethernet, which is that it eliminated the need for users to configure addresses. Every piece of equipment that plugs into an Ethernet comes configured by the manufacturer with a 6-byte unique ID. And just a rant, for bizarre reasons, this built-in address is known as the MAC address. So first of all, to me, an address is something that should change if you move to a different place. But this is a built-in thing, so it really should be called an ID because it never changes no matter where you are. And then it's a MAC address. So what is a MAC? And don't worry about it. I know what it is, but it's just silly, pompous standards body jargon. So I saw Ethernet as a new type of link. So I said, oh, wow, I have to modify the routing protocol to accommodate this kind of link. So for instance, with link state routing, if you have an Ethernet with 500 nodes and everyone reports 499 neighbors, then the link state database gets really big. So instead, I introduced the concept of what I called a pseudo node, which is that I said, suppose the Ethernet itself was a new node and everyone just has to talk about how they're connected to the Ethernet rather than to each other. So instead of having a fully connected topology like that with all of those links, instead you have n+1 links and only n+1 nodes and only n links. So I saw Ethernet as a link in a network, not a network, and I wish they'd called it Etherlink. So a layer 3 packet has a destination, a source, and a hop count. An Ethernet packet looks sort of the same, but it doesn't have a hop count. Now, why doesn't it have a hop count? Well, it wasn't that the Ethernet designers didn't know about hop counts. It just never occurred to them that anyone would be forwarding this packet format. It was supposed to just be on a single link. And without forwarding it, you don't need a hop count to notice when there are loops in the topology and packets are getting lost. So how did it evolve from CSMA-CD to a spanning tree? Well, people built applications directly on Ethernet without layer 3. Now, you can't put a router there. It can't forward Ethernet packets without having the end nodes put in a layer 3 header. So I did try to argue with them, say, no, you still need layer 3. And they said, oh, Radia, you're just upset because no one needs your stuff anymore. It's now going to be Ethernet. And I said, oh, but you may want to talk from one Ethernet to another. They said, our customers would never want to do that. So the applications they built were good, and the implementers were considered heroes because they made lots of money for the company, but they would have made just as much money if they had done it properly with layer 3. So my manager, years later, about 1983, he said, oh, Radia, you do distributed algorithms. We need to design a magic box that will sit between two Ethernets and let someone on one talk to someone on the other, which is what my stuff did, but it required the end nodes to be aware of it. So the constraint was without modifying the end nodes, which think they're just talking on a single Ethernet, and there were no spare fields in the Ethernet packet, and there was a hard size limit, design something. So the basic concept was the bridge just listens what's called promiscuously, which means it listens to every single packet and then forwards that packet to all the other ports when the ether is free, or if it's a token, it gets a token ring. This requires a topology without loops. So what to do about loops? We could just tell customers, don't put in loops. But what if they make a mistake and miscable it? Or what about backup paths? Loops aren't bad. It just means that if something breaks, you'll have another way to get there. So there was a desire for a loop pruning algorithm where my manager said, you should allow any physical topology. You should prune to a loop-free topology for sending data. And this was the birth of the spanning tree algorithm. So you plug something together. These round things are bridges, the blue things are Ethernets, and the black things are ports from the Ethernet, from the bridge to an Ethernet. Once the spanning tree algorithm runs with the bridges doing it amongst themselves, they'll turn off some of their ports, which means they will not forward data to and from it. They'll still be running the spanning tree algorithm. So with that topology, if A transmits to X, the path will be this long path. And you might think, well, if the spanning tree algorithm were more clever, then you'd get better paths. But no, if you have a single shared topology, then someone's not going to get good paths. The spanning tree algorithm has to chop the circle someplace, and guys on either side of the circle have to go around the long way. So everyone knows Ethernet is wildly successful. And when I hang out with some of the old timers, they say, oh boy, it sure is lucky that the industry didn't go with that silly token ring or token bus way of sharing a link. But wired Ethernet is quickly became spanning tree with point-to-point links after we launched this bridge product. And so Ethernet today has nothing to do with the original CSMA CD invention. There's no clever way of sharing a link that's needed. So, even if it's all point-to-point links, the spanning tree algorithm can shut off some of the things. So the manager asked me to do this on a Friday. And as a challenge, he said, not only should there be zero configuration and no topology rules, and it should also scale as a constant. So no matter how many bridges and links there is, the amount of memory necessary to run this should be a constant, which is crazy. Nothing is a constant. It's probably going to be n squared or at least linear. And that night, he left for a vacation for a week, and this was before email or cell phones, so there was no way to reach him. And that night I realized, oh my goodness, it's trivial. And furthermore, it scales as a constant, because if you're a bridge, all you have to do is remember the best spanning tree message you've heard on each of your ports. And and when you receive a spanning tree message, you look at the one you have stored for that port, and there's a trivial comparison to see which one's better, and you keep the better one and throw away the other one. So I was very excited. I finished the specification by Tuesday afternoon. It was about 25 pages. It was complete enough that when the implementer started implementing it, It it only took them a couple months to implement it without asking me a single question. So now I was all excited and I couldn't concentrate on anything else without being able to show off to my manager, and he wasn't around. So I spent the remainder of the week working on the poem that's the abstract of the paper in which I published this. So the poem is called Algorhyme because every algorithm should have an algorhyme. So I think that I shall never see a graph more lovely than a tree whose crucial property is loop-free connectivity, a tree which must be sure to span so packets can reach every land. First, the root must be selected. By ID, it is elected. Least cost paths from root are traced. In the tree, these paths are placed. A mesh is made by folks like me, then bridges find a spanning tree. So yeah, I'm going to skip this because I'm running. So you can just trust me that the spanning tree algorithm is incredibly trivial. So then should we force the implementers to implement it? Even though it's trivial, it still makes the bridges more complicated. Maybe just tell the customers don't do loops. And so I let management argue, and they said, no, you can't ship a bridge without putting in the spanning tree algorithm. And then when we sold the first bridge, I realized, yes, that was the right decision. So the first bridge was sold to the world's most sophisticated networking customer, and the sales guy was saying, oh, it doesn't matter what you're doing, it's just going to work. And they said, no, we need to talk to the engineers. And the sales guy said, no, you don't. And then they plugged it together and it didn't work. So the world's most sophisticated networking customer with the world's simplest topology had done this, which is they plugged both ends of the bridge into the same Ethernet. And I'm glad I thought of that case. So the bridge was saying, oh, I don't need to forward packets. I'm here if I ever need to. So spanning tree Ethernet is a kludge. You don't get optimal paths. Unused links, those that are not selected to be in the tree, are underutilized. Temporary loops are really dangerous because the header has no hop count, and bridges, when it forwards a packet, if it has more than 2 ports, it'll multiply the number of copies. So why was bridging so popular? So originally there were lots of layer 3 protocols, IPX, AppleTalk, etc. So you would need to have a lot of different routers. Now, some people built multi-protocol routers, but they were expensive and slow, whereas bridges just worked and they were cheap and didn't require any configuration. Now, as it turns out, bridges really helped IP become more tolerable. So a question, can I go over time here? Oh, well, I'm going to assume.
Yes, please.
Okay. Yes, since this is the first time I did the talk in this, I couldn't quite tell how long it was going to be. So now let's go back to why do we need both Ethernet and IP? Why can't we get rid of Ethernet and use only IP, hook everything together with IP, given that we don't have any CSMA-CD links? So the world has converged to IP as layer 3, and it's in the network stacks. So the original reason for needing bridged Ethernet is gone. On a link with just 2 nodes, why do you need a 6-byte source and a 6-byte destination address just to talk between 2 nodes on the one link? Why can't you forward things with layer 3? And if IP were designed differently, we wouldn't need the Ethernet header anymore. Now, there were other layer 3 protocols that could have done all the link forwarding with a true layer 3, which was designed for being forwarded. So what's wrong with IP? It's configuration intensive. You can't move, like, for instance, a virtual machine. If you move from one side of an IP router to another, you have to change your layer 3 address. Routers need to be configured with which addresses are on which ports. So you can't have a cloud with a flat address space where you can move around without changing your layer 3 address. So with IP, every link has to have a different address block, and the router has to be configured with which addresses are on which port. But layer 3 does not have to work that way, and this is something that I wish people would understand. There was a competitor to IP known as CLNP, Connectionless Network Layer Protocol. And we adopted it for DECnet. It was a 20-byte address. So there's not that much in a layer 3 header that matters. It's a destination, a source, and a hop count. So that's what CLNP was, but it was a 20-byte address. And this was, back in the 1980s. Now, what's important about this is that there were two types of routing. The top was 14 bytes, and it was a prefix shared by all nodes in a large cloud. So that kind of routing worked just like IP in that you can have as many levels of hierarchy as you want. But once you get to a cloud, all of the nodes in the cloud share the same prefix, and then routing goes to the individual nodes within that cloud. So the nodes inside the cloud had to announce themselves so the routers would know where you were inside the cloud. So with the 14-byte prefix, the prefix lets you have as much hierarchy as you want. And then instead of ending on what IP perceives as a link, you end on a cloud that has lots and lots of links. So once you get to the cloud, you route based on the bottom 6 bytes. So if you're doing IP plus Ethernet, IP gets you to what IP thinks is a link. And then you need to shout with this protocol known as ARP, saying, hey, can you tell me what your layer 2 address is inside this cloud? And inside the cloud, if you want to have multiple links, you have to do something like CSMA-CD or spanning tree or other things. Whereas with CLNP, you get to the cloud and then you just route based on the bottom 6 bytes. You don't need to find out what your address is in the cloud because it's part of your 20-byte address. And inside the cloud, you have true layer 3 routing with a hop count and all the good things that layer 3 routing does. So in terms of configuration with IP, everything has to be configured, whereas with CLNP inside of a cloud, you don't need to configure anything, except somebody has to know what the prefix is for the cloud and let everybody else know. So one of the worst decisions ever was that in 1992, people said, hey, the internet should adopt CLNP. It's a 20-byte address. The IP addresses are too small. And someone modified TCP to work on top of CLNP. It only took them a month or two, and that meant that all the internet applications would work with CLNP because they all worked on top of TCP. And it was so much easier to move to a new layer 3 back then. The internet was smaller. It wasn't so mission critical like it is today. And IP hadn't yet invented things like DHCP and NAT, which I'll talk about. So CLNP gave understandable advantages. So CLNP is so much cleaner than IP, including IPv6, because of this ability to have this bottom level of routing where you could have a cloud with lots and lots of links. So the reasons given at the time not to adopt CLNP was, well, it would be ripping out the heart of the internet and putting in a foreign thing, which is nonsense because there's nothing more compatible about IPv6 than CLNP. It was basically, it's just, we didn't invent it. We don't want to give another standards body the satisfaction of saying that something they did was worthwhile. Or we don't like ISO layer 6, and that's fine. That's not what's being proposed. We're just proposing replacing the layer 3 with ISO's layer 3. And they said, well, we're not immediately out of IPv4 addresses, and we're geniuses, and all the other standards bodies are all morons. So I'm sure we could invent something way more brilliant. So the decision was, let's do something new and call it IPv6, which is just a 16-byte version of IP with 8 bytes for prefix and 8 bytes for the node on the last link, where 8 bytes on top is inconvenient. It's hard to administer global addresses, and 8 bytes on the bottom is way too much. So anyway, it's technically inferior to CLNP because, again, if you move from one side of an IPv6 router to another, you have to change your layer 3 address. So here's some good stuff that may not have happened if the industry had made the right decision. So DHCP, Dynamic Host Configuration Protocol. So with CLNP, how do you get a layer 3 address? You take your Ethernet address and stick it into the bottom 6 bytes of your 20-byte address. With IP, originally, you needed to configure every single node with its IP address. And then they invented DHCP, where there's a server on the cloud that has a pool of IP addresses. And when a node comes up, it says, hey, I need an IP address. And the DHCP server says you can have this IP address. So what's cool about DHCP is you don't need to have 6 bytes for the address on this link, which means that addresses could be smaller or the top part could be bigger. It enhances privacy. Something that people noticed years later was that if you put your Ethernet address into your thing, then someone that knows the Ethernet address of my machine can see a packet on the internet and say, oh, I see, this is Radia, and she seems to be visiting Malaysia this week. But with DHCP, since you get kind of a temporary local address, then nobody can know that it's my machine. So certainly you could have used DHCP with CLNP and it would have been preferable, but would anyone have thought of it because CLNP already had auto configuration? And the other really cool thing is NAT, Network Address Translation. So IPv4 clearly can't possibly number all of the nodes in the internet. So what they do is they have like a block of addresses that lots and lots of little networks use the same block of IP addresses. So that wouldn't work very well because how would you be able to find something? But it works fine within the little private network. But there's this NAT box that has some globally routable addresses. So if G wants to talk to somebody that has to have a global address, Z, then the NAT box says, oh, okay, if he wants to talk outside here, I better give him a one of my addresses. And so he assigns it K. So he overwrites the source address with K. And when the return traffic comes, then the NAT box has to replace K with the local address, which is G. So this is really great because for security, because there's no way to talk to a node unless it talks first. And certainly that could have worked with CLNP, but would anyone have thought of it since global addresses were plentiful? So in summary, if you try to understand network protocols as they are, it won't make sense. Why does it have to be this complicated? The only way to understand it is to hear about the history. Nobody would have designed what we have today. It's just sort of evolved, what's the smallest thing we could do to solve our immediate problem or mistakes that standards bodies do. And it's kind of astonishing that things work as well as they do. So I think a good analogy is like English. It's a terrible language, but it does the job. So people aren't motivated to replace it with a better language because you can kind of do what you need to. And that's kind of the way IP is today. So thank you. So that is the talk. And now I can look to see if there's anything in the chat and let people ask questions.
Yeah. Thanks, Radia. That was quite a lot. But I'd like to ask this: if these nodes are all receiving all these numbers, they're decoding the numbers, deciding they're not them, and passing them to the next node, the next node, and next node. It's amazing that we get an almost instantaneous response from where you are and where I am.
Right. But there's all sorts of ways for networking to get screwed up, especially with the BGP protocol, which is very configuration intensive. And that's another whole thing I could rant about. There's sort of no excuse for having BGP. It's a really bad protocol. It's very slow. It's very configuration intensive. It's very fragile. And if the world had just, they say, well, they need it for scalability. No, you don't. ISISQ can have as many levels of routing as you want. So it isn't for scalability. It might be for policies. Now, when I complain about BGP, people say, well, can you design something better? And I'm sure I could, but I don't like to solve things before I know what problem I'm solving. So I say people should write down what are these policies that you absolutely need. And unfortunately, the world has kind of been polluted with knowledge of BGP. They'll just say which knobs in BGP they're using rather than what are the policies you really need. So at any rate.
Yeah, that's one. The other thing that I noticed on the sender's address and receiver's address, it sounds very much similar to actual communication-based time division multiplexing, multiplex access, TDMA, where we do have a header address and a sender address and what do you call this error correction and all those stuff. And I was just wondering, how does when you design your net protocols, do you design for this to be working together, or they just two separate stuff?
Well, I considered a link to be let its link do its thing. And I was worried about how to go from link to link to link. So yeah, there's various wireless technologies, and those are great. It's not necessary really for layer 3 to worry about
The
what
physical,
kind of
yeah.
multiplexing is
Okay,
done
okay.
on those
Yeah,
links.
right. Yeah, right. Okay. There's one by Mr. Fairoz. Does this consider SEO poisoning?
Let's see if I okay, is what I don't know what SEO poisoning means.
Mr. Fairoz, do you want to explain yourself? You want to ask a question?
I think it's about search engine, the search engine poisoning.
Oh, are you talking about BGP? Yes, indeed. There's lots of ways of subverting BGP. I'm also not sure what this means in the does this consider as SEO poisoning?
Think about the cyber attack technique, something like manipulate search engine, something like this. I think probably that question about that one.
Yeah, well, people can send me email if you want, but yeah, I'll defer that question for now, I guess.
Fairoz responded, the one that appears on top during searching on Google.
Ah, a search engine poisoning. Yeah, it just has some sort of algorithm for deciding what should be first. The easiest one is to just buy it, and then it says add if you pay the search engine company. But I'm sure that if you understand the algorithm and you create a lot of websites that all point to your website, that you can make your site, your criminal site, appear high in the order.
Does that mean all those scammers and criminals are PhD holders?
No, I think one smart person figures it out and then lets other people, other
Not so
criminals
much
know.
on the technicality, but more on the gaming of the stuff. Okay, okay.
Right. Whoever figures it out first is
Yeah.
probably reasonably
Right,
clever.
right, right.
But yeah, no, these criminals are all pals with each other and they share techniques.
Okay. If you were asked to redesign the internet from scratch today, with all the bells and whistles of what we have today, modern computing power, AI, cloud computing, all those cybersecurity challenges, what would you do differently?
Ah, well, 10 years ago, I would have waxed rhapsodic about the miracle of the internet, that you can talk to anybody anywhere in the world. You can find a group of people who are interested in your weird hobby. Um, but these days, I think the internet is basically the end of civilization. So, like it's great that you can find information on anything, but you can also find misinformation. It's very difficult to find the difference, in which case it's not useful anymore. If
Mm.
you can't distinguish the correct stuff from the incorrect stuff, and it basically is polarizing society. There are all these algorithms that say, oh, you like that type of stuff. Well, I will feed you even more and more of that. And I won't ever bother you with stuff that, isn't
Mm,
what you
mm,
already
mm.
believe. And so it's very terrifying. So, what I tell students is, yeah, that sounds really scary, but what would be even more scary is if I were to give a talk and say, we have solved everything. We're giving you this perfect, wonderful thing. There's no more problems to solve. That would be terrible. But here, if we're saying we're giving you this incredibly, disastrously broken thing, and you have all these opportunities to improve it, that's a good thing.
Okay.
So
On
someone asked about the spanning tree. It's really
Yeah.
successful. And of course, it underutilizes network resources. At the time, I thought it was the wrong thing to do. I was arguing, yeah, this is a cute thing, but instead just fix the end nodes to put layer 3 in there. Because spanning tree is a kludge in various ways. Um, but they said, well, it'll take us a few months to fix the end notes. So in the meantime, this will make some customers happy. So I thought it was going to be something that was going to work for a few months, and then the world would do it the correct way. But given that the world did not adopt CLNP, um, and IP has this, real problem that it's so configuration intensive and you can't move around from one side of a router to another. That's why spanning tree is still incredibly popular. Now, if instead we had CLNP, we could get rid of spanning tree because everything would be hooked together with routers. So,
Yeah, on a different note, students see networking as a practical engineering subject rather than a mathematical one. How important has mathematical thinking been in developing all these routing algorithms?
Well, okay, I don't remember anything that I learned in math, but what math did teach me is how to think cleanly. So when I went back to grad school in computer science, um, I figured I had never taken computer science classes, so I should force myself to do that. Um, and I was kind of horrified because in math, you can ask a professor a question like, what's a number? And they'll give you a clear answer. Whereas in computer science, there's all these buzzwords and they invent new buzzwords for things. So I remember asking, what is object-oriented programming? That was like a big deal back then. And the professor was just shocked because everyone knows. No one had actually like asked him that. And um, So he was saying, well, it's a way of thinking. And it's like, well, what's different about it? So when I finally figured out what it was, I was saying, okay, so you're saying it's a good idea to have a library of well-defined subroutines with well-defined inputs and outputs. I knew that already. Why do we have to give it a new word and call it methods and whatever? So yeah, computer science people tend to start using buzzwords and no one really knows what they mean. So once I was at a meeting of very senior people, and we were at tables of like 10 people, and someone gave a talk about how wonderful cloud native was. And so after the talk, I asked the person next to me, and we're all supposed to be senior technical people. I said, I still don't know what cloud native is. The speaker was just talking about how wonderful it is. Can you explain it to me? And he laughed and he said, I have no idea. And we went around the table and nobody at our table had any idea what that meant. I mean, I could imagine a bunch of things you could apply that label to. But yeah, that's something I think that's bad about computer science people, is that they kind of think muddily, whereas math kind of teaches you to get to the conceptual heart of things and not just say, oh, well, we'll apply zero trust principles, where no one really knows what you're talking about.
On a personal note, you said you had gone back to your graduate school, PhD, after about 10 years. I find it quite incredible that you are not pulled by the dark side of money and luxury in life. What propelled you in that direction?
Okay, well, that's kind of an amazing story. So I had very young kids, and I always had the world's worst cold. So wherever I went, I had to carry a large box of tissues and a waste paper basket, and I was constantly blowing my nose, and it was just disgusting. And I would, and my eyes were just running, and my face was all puffy. And I mentioned to my manager, I was a little embarrassed and I was afraid that people would think I was upset. Now, my manager was very smart, but no clue about the proper way to interact with people. So at this point, he should have said, oh, no one would think that. It's obvious you have a cold. But what he said was, yeah, I was wondering why you always looked upset. But at any rate, I would stay home a few days and feel a little better, and then I would go back, and I just couldn't shake the cold. So I eventually went to a doctor, which I never do, and I said, I know I'm not getting enough sleep, and I'm doing too much. None of that's going to change. Just give me some sort of drugs to help me get rid of this cold. And he said, well, how long have you had it? And I said, oh, I don't know, maybe 4 years. And he said, yeah, that's not a cold, that's allergies. And with a bit more detective work, I realized it was cigarette smoke, that I had never been around until I went to digital. And so I complained to HR and personnel, and they said, well, they'll make sure nobody in any cubicle next to mine is a smoker. But what's your problem, lady? Only a third of our employees smoke. So back then you could sit at your desk and chain smoke. So I was telling my friends, I'm going to have to quit. It's just exhausting being sick all the time. And they said, oh, be patient. Digital is aware of the smoking issue and they're working on it. So back then, Digital had this amazing program where they would pay for 2 years of graduate school, all expenses paid, full salary, no strings attached. So I decided, okay, I will go hide out in grad school for a couple of years and let them work on the smoking issue. So indeed, I managed to get my PhD in 2 years. I actually set a record in the computer science department. And I came back with my PhD, and they had solved the smoking issue by issuing a memo that said, quote, don't smoke in the building, unquote. I have no idea why this took them 2 years, but thank you, Philip Morris, for my PhD.
Okay. All right. So that means you went back to DEC after your PhD?
Yes, and
Or
I didn't even have to. There was really no strings attached. But
okay.
at any rate, I was still being paid as much as I did before during grad school. So when you were saying, "Gee, I had to give up money," no, I did not.
Okay.
And
Okay.
had I gone to graduate school right after undergraduate and finished, I would have become a professor because I absolutely love teaching. So now I teach as a hobby whenever I get a chance.
Okay. That brings me to an interesting point. How much did uh, years at DEC poison your thoughts on or the idea development that the PhD uses?
Okay, your audio was cutting out. Can you say it again?
Oh, sorry. How much did DEC the work experience at DEC poison your idea development for a PhD?
It didn't poison it. It was incredibly valuable.
Okay.
So when I went back, I sort of knew more about networking, especially network routing. I didn't really need an advisor at that point. So it was a great experience
Okay.
when I went back the second time. Yeah.
All right, all right. So, and nowadays, are you doing about the same thing as what you were doing at DEC? Are you doing the same thing at Dell, or just uh, a bit more towards training?
Oh, I'm doing much more security stuff. So when I joined Dell, I joined this company called EMC that Dell bought, and that was a storage company. So yeah, I have designed all sorts of cool things for making storage more secure and um, efficient and things like that. So yeah, whatever the problem spaces, it's really fun. And I really like distributed algorithms where it's not just, one program, it's how to make a bunch of things interact with each other.
Oh, security. All right.
Yeah.
Yeah, that reminds me, radio program I heard a week back here in Malaysia, where they were interviewing a French defense company, and the guy and I was surprised that the guy said we are watching what's happening with the quantum world, and that brings back to what you said about breaking the RSP crypto keys. So they're saying maybe what we're doing at 128 and 256 is not enough, and we have to come up with new algorithms for defense-based securities.
Okay, well, I'm glad you gave me the opportunity to answer that. So there are misconceptions about quantum computers. Most people in the industry sort of believe that any program that runs on a classical computer will run a jillion times faster on a quantum computer.
Yeah,
This
yeah,
is absolutely false.
yeah,
There's very few things that actually would run faster.
yes.
So it turns out there's one algorithm that would run on a quantum computer called Shor's algorithm, and it can factor numbers and it can do discrete logs, whatever that is, doesn't matter. But that happens to break all of our current public key algorithms, like
Mm,
RSA and elliptic
mm,
curves. But it doesn't affect things like hashes and secret key algorithms. There is another algorithm that would run on a quantum computer known as Grover's algorithm that actually allows a brute force search in the square root of the size that you might think. So 128-bit key brute force search on a quantum computer would be half of that, so like 64 bits. And you
mm.
might think, well, we can just apply Grover's algorithm multiple times. No, you can't. It at most halves the size of the key. So basically, what the cryptographers said was 128 bits is secure enough for anything except for this Grover's algorithm on a quantum computer. So, okay, we're going to start using 256-bit secret key and 512-bit hashes. And so fine, don't bother us anymore about Grover's algorithm. Like what we have for the secret keys and the hashes are good enough. Quantum is not going to affect that. And it's only the new public key algorithms that are an issue, and they have perfectly good ones. They're unbelievably cute once you understand them. And I haven't seen any place other than our book that explains what's actually going on. There are specifications and you can implement it from the specification, but it doesn't actually explain what's going on. So there are algorithms, and the industry will be replacing our current ones, even if there's never a big enough quantum computer to threaten our current size of like RSA. It doesn't matter. Your stuff will not be bought anymore. Customers will say, oh, you're still using that old stuff. So the industry is very soon going to move to the new ones.
Okay, I think we have one unanswered question by Dr. Nurfaiza. Dr. Sharifah, what do you consider the biggest misconception engineers have about routing and bridging?
Well, I think that the way networking is taught is as if TCP/IP arrived on tablets from the sky in its awesome perfection. And so, they've learned this is how things work, and it doesn't occur to them that there were any other ways of doing things. It's just you have to work with what's there. And yes, you do have to work with what's there, but it would be really nice if people could understand some things such as, we shouldn't need spanning tree. We shouldn't need Ethernet anymore. We should just hook everything together with layer 3, and why IP doesn't do that very well. The things that I talked about in the class, most networking people would not actually know these things, even though they've been working in the industry for years.
Okay. All right, Dr. Radia, thank you very much for freeing us from the tangles of the net. Before we bid you farewell, we'd like to have a group photo with you and our listeners. So if everyone online, could you please switch on your cameras, and Mr. Shah can take the pictures. Everyone, cameras, please. Cameras, cameras, cameras. Cameras, cameras, cameras.
So thank you so much for inviting me. You can tell I really love giving talks like this. I wish I could have met each of you in person.
Yes, you could always come over.
I
Please do
think
visit
Malaysia
us.
is far away, but I'll have to look at the map.
You just need a header address and a sender address.
Right. I get on the plane and assume the plane will know how to get me there.
Cameras, please, guys. It was an absolute pleasure having you around, giving us the breakdown on all this stuff, routers and bridges. Wait, half the cameras are off. Come on, guys.
They're shy.
This is the first time.
Do you always do this? Ask people to turn their cameras on and get a group shot?
Yes, yes, yes. At the end, yes.
Well, in the meantime, I can read the
Cameras, please,
chat.
guys. Yeah, you can read the chat. There was one thanking you. Thanks, Prof. I really admired your step by creating a loop-free bridge inverted tree topology in a redundant network.
Okay, done.
Done? Okay, all right. Thank you. Thank you. Thank you, guys. And thanks, Radia. We wish you a very good night and thank you very much. Dr. Nazri will be in touch with you with our certificate of appreciation. Hope you had a good time with us, and we didn't take too much of your time. Thank you very much.
Okay, thanks.
Right.
Bye.
Bye-bye.
Bye. We'll be in touch for the lecture series, communication and all that stuff. Yeah.
Ah, I'm not hanging up because I like seeing all these nice thumbs up and hearts and things. It's very nice.
That was a good one. Okay. Fine.
So I probably should hang up or else nobody else will hang up.
Go for July. Right? Where'd you go for 4th of July?
Recording
stayed home.
stopped.
Yeah.
Oh, okay.
I don't really think about
250.
Oh,
holidays.
250 years,
I'm
yeah.
always working on a book or something.
Okay, all right.
But the last place we went on holiday, we went to